All right, let's look at vectors. Vectors are lists of numbers. For instance, vector v, and for the variable of a vector, we put an arrow on top to symbolize that it is indeed a vector. Will look something like this. We have some first element we can call x1, then some second element we can call x2, and it keeps going for as many elements as we want, all the way to xn, where n is the number of elements that you have. The reason I use the term list is because in vectors the order matters. For instance, this vector v1, which includes the elements 7, 10, and 8, is unique from this vector v2, which includes the same elements 7, 10, and 8. However, they are in a different order. So we say vector v1 is not the same as vector v2. Vectors have a dimension. A dimension is simply the number of elements in a vector. So for our vector 7, 10, 8, it has 3 elements. So we say the dimension is 3. A more formal way of saying this is the dim or dimension of vector v is 3. One of the important operations that we can perform on vectors, just as we could perform on ordinary numbers, is addition. This is how vector addition works. One vector plus another vector. To get the sum, we add the corresponding elements. So when we add these two vectors, we get another vector where x1 is added to y1, x2 is added to y2, and so on, all the way to xn and yn added together. As you can see, in order to add two vectors, they must be of the same dimension. Here's an example. If we have 7, 3, we can add that to vector 4, negative 1. We get 7 plus 4, which is 11, and 3 plus negative 1, which is 2. So the result of adding 7, 3 to vector 4, negative 1 is 11, 2. Now here's an example of why we define vector addition this way. Say a vector represents inventory. So this vector v, the first element, represents the number of eggs we have in our inventory. The second element is the number of carrots we have in our inventory. And the third element is the number of onions we have in our inventory. So for instance, we could have the vector 7, 2, 1, which means we have 7 eggs, 2 carrots, and 1 onion. Right? In real-world situations, you have to define what the elements of your vector mean. And in this real-world example, each element corresponds to a different product in our inventory. But let's say we get a new shipment, and we get one more of each item. How could we represent this update happening? Well, we could create a new vector, we'll call it v star. And we can take our old inventory, 7, 2, 1, and add our update, which is one of each. So it's a vector that contains all ones. And that updates each element, right? Because vector addition, each element gets added to each corresponding element gets added together, and we get our updated inventory, which is 8, 3, 2. Now multiplying vectors by a constant. When you multiply a vector by a constant, you're really just adding it, the same vector, to itself a certain number of times. And if you think about this, all it means is we apply that constant to each element in our vector. So for example, if I have 2 multiplied by 5, 1, that really means 5, 1 plus 5, 1. Or another way of thinking of it is applying the 2 to each element. So we get 10 and 2. Now you may be asking about subtraction of vectors. Well, subtraction is really just adding a negative. So for instance, 5, 6 subtract 1, 2 is really just 5, 6 plus negative, the negative 1, 2 vector. And a negative outside just means multiply by negative 1. So we can multiply the 1, 2 vector by negative 1. And we get negative 1, negative 2. And now we can just do this like a normal vector addition problem. We can also have functions of vectors. Just as we can have functions where the input is a real number, we can have functions where the input is a vector. For instance, f at x vector is equal to 2 times x vector. Let's say we put in the vector 2, 1 as the input. Well, we get 2 multiplied by 2, 1. So the output would be 4, 2. So this operates just like a normal function. It's just that the input is a vector and we use the vector operations. Now, just as we can have linear combinations of real numbers, we can have linear combinations of vectors. For instance, let's say we have vector 1, which is 3, 4, and vector 2, which is 1, 3. Here's an example of a linear combination of these two. We could have 2 vector 1s and add those to 3 vector 2s. If we do the math here, we get 9, 17. The really important fact here is that 9, 17, we say, is a linear combination of vector v1, which is 3, 4, and vector v2, which is 1, 3. So 9, 17 is a linear combination of those two vectors. Now let's revisit linearity. We talked about what it means for a function to be linear, and the same definition applies to functions of vectors. We can just write arrows on top of all our variables. So we have the same definition, just with vectors.